1 2 1 2 1 2 3 4 5 1 2 3 4 5 1 2 3 4 5 1 2 3 4 5 1 2 3 4 5 1 2 3 4 5 1 2 3 4 5 1 2 3 4 5 1 2 3 4 5 4 5 4 5 1 2 3 4 5 1 2 3 4 5 1 2 3 4 5 1 2 3 4 5 1 2 3 4 5 1 2 3 4 5 1 2 3 4 5 VK3CSJ testing. Hello test. Hello test. Hello test. 1 2 1 2 1 2 3 4 5 4 5 4 5. It's not perfect. 1 2 3 4 5 4 5. Hello, hello. I can hear distortions. 1 2 3 4 5 5 1 2 3 4 1 2 3 4 5. Hello test. 4 5 4 5 4 5 4 5 4 5 4 5 4 5 4 5 4 5 4 5 4 5. VK3CSJ testing. Hello test. 1 2 4 5 4 5 4 5 4 5 4 4. It will have to do. Stand by for the ASV broadcast at 10 o'clock on these airs. VK3CSJ. Thirty seconds. Ten seconds. Good evening. This is VK3EKH, VK3 Echo Kilo Hotel, the official station of the Astronomical Society of Victoria, with the regular Friday night broadcast coming to you from the studios of VK3CSJ in Narre Warren South. We're broadcasting on prime frequency of 3541 kHz in the 80 metre amateur radio band, and also via the Melbourne television repeater, VK3RTV Digital Channel 1, and also on my 2 video streams, the Discord channel, HD channel, and also on my YouTube channel, which is VK3CSJ. Just type in VK3CSJ in the search engine, YouTube search engine, and look for the live indication. Hopefully the streams will hold out tonight and will not fall over. We have a email address, vk3ekh@gmail.com, if you wish to send signal reports and the like to vk3ekh@gmail.com. All right. What else is there? I think that's about it as far as transmission goes. I feel like I'm missing something, but anyway. All right. The usual blurb on this 18th of July is perhaps what I forgot to mention. All right. Hope everybody is feeling okay for this end of the week. Right. Let me see. The Astronomical Society of Victoria was founded in 1922, has well over 1,800 members throughout Victoria and Australia. Overseas membership. Membership of the Society is open to all persons with an interest in astronomy. The Society's objectives are to encourage the study and practice of astronomy, and to disseminate the knowledge of the science, and to provide greater facilities for the study among its members. Monthly meetings are usually held on the second Wednesday of each month, except in January, with the latter being held on a Saturday night. Meetings start at 8 p.m. at the Mullier Hall, Burwood Avenue, Melbourne, near the Melbourne Observatory, which is located not too far from the Shrine of Remembrance. Meetings are also live and streamed on YouTube and the Facebook video channel dedicated to ASV. Parking is available in Burwood Avenue, Dells Brooks Drive, and the surrounding streets. Admission is free and visitors are most welcome when the meetings are conducted at the National Herbarium. Privileges of membership include the right to borrow books, periodicals and other publications from the Society's extensive library located at the Melbourne Observatory, receipt of the ASV magazine Crux containing articles, news, observing notes and the like, and the free provision of the Astronomical Yearbook. Access is available to telescopes on members' nights held regularly at the Melbourne Observatory and after the monthly meetings, weather permitting. These instruments include the Society's 300mm equatorial reflector and 300mm portable reflector. There's a 200mm refractor managed by the Royal Botanic Gardens, and a photoheliograph are also housed at the observatory and are accessible to members as well. The Society also has a number of 200mm reflectors available for short period loan in the ASV telescope loan scheme. A member can gain practical experience in the use of one of these telescopes before deciding whether or not to buy one of their own. Regular Society meetings are held at the Morley Community Village in Bentley East. Members are encouraged to use the Society's instruments located there in order to gain first-hand experience in telescope use. Members are also encouraged to make use of the Society's country property located near Heathcote, some 90-minute drive north of Melbourne. It provides dark skies suitable for astrophotography. Trying not to sneeze here. There is a range of instruments available for members to use, the larger two with appropriate training, which range from 300mm to 1000mm in aperture. Also located on site is a fully steerable 8.5 metre radio telescope, which members can access with involvement with the radio astronomy section. Members are encouraged to make and use telescopes. Advice and help on both matters are provided willingly to newcomers desiring to do the same. Instrument making is only one of the several common interest activities catered for within the Society. Other areas of interest that members can participate in include deep sky observing, astrophotography, lunar and planetary observing, auroral, meteor, comet, radio astronomy, computing, cosmology and astrophysics, historical studies and research and astronomy in general. Contact details for various section directors can be found on the ASV's website at www.asv.org.au. Further information may be obtained by visiting the ASV website, and notifications of events are given in the Crux Extra Bulletins sent out via email to members every other week. Please note that the ASV will conform to any government health directive, thus ASV events may be required to be cancelled, moved or postponed. That's the usual blurb I say every week. This is, for those watching the video, this is the yearbook, Astronomical yearbook, which ASV publishes every year and has been doing so for a long time. It's full of absolutely amazing information for the optical astronomer and for anybody wishing to study and research astronomy in general. The Crux magazine, which also is produced by ASV, is this guy here. I think that's the recent one that's come out. So it's full of information as well. Anyway, so like I say, further information can be found by going to the ASV website at www.org.com.au. Alrighty then. I've got a few articles tonight. Hopefully they won't go for too long. Now, last Friday, I missed the opportunity of letting folks know of the monthly meeting. As I said during the intro, there is a monthly meeting every month, second Wednesday of every month. If it can be, it will be held at the National Herbarium in Melbourne, which is probably the better venue. More personal. You can be there and see the person doing presentation directly. But these days, of course, it's also broadcast on YouTube and Facebook. This month's monthly meeting was, in fact, this Wednesday, just gone. And I think I might have mentioned that actually last Friday. I can't recall really, but when I went looking for who was doing the presentation, it really wasn't there on the calendar where I normally source my info for that sort of detail. And but it's there now. So what transpired last Wednesday night was an interesting presentation. I didn't see it, but I have downloaded it, and I plan to screen it after the broadcast tonight on the various video mediums. But this month's Astro Talk was presented by Sarah Caddy, and Sarah Caddy was exploring the rapidly growing challenge of space domain awareness as more satellites are launched this decade than in all of human history combined. The need to track, identify and monitor space objects is more urgent than ever, both for astronomers dealing with light pollution from satellite trails and for operators protecting critical infrastructure like GPS, communications and disaster response systems. Sarah will outline the cutting-edge work being done by the University of Melbourne and Macquarie University to tackle these issues, and how amateur astronomers can play a valuable role even with discarded images featuring satellite streaks. And of course, following Sarah's talk is Bill Stent's talk on the sky of the month for June and July, which I may feature as well. Sarah's talk, I very quickly checked the time, and it looks like Sarah's talk only goes for about 40 minutes, I think, from what I could see, and then that was followed by Bill Stent, the telephone, why am I saying that? The telescope gent, the sky for June and July. So, and that usually goes for about 15-20 minutes. So I may run it the entire lot, but I'll plan is to run it as soon as we're finished with the broadcast tonight on the various video streams, and including the TV repeater. So if you wish to stand by, hang around afterwards, we'll play the Astro Talk that occurred on Wednesday night, featuring Sarah Caddy, and of course it's introduced by Mark, the president of the. I was about to say United States. I'm not with it. I can see that already. President of the ASV. I'm sure Mark has good circulation. Anyway, all right, so that's the Astro Talk that has been gone last Wednesday. If you can't hang around after the broadcast, just go to the YouTube channel, ASV's YouTube. Just type in Astronomical Society Victoria, and you'll be very quickly brought up to the ASV's YouTube channel, and you'll see last Wednesday's talk. You're tuned to ASV Radio, VK3EKH. As I have been in recent weeks, been giving the Southern Astronomer a bit of a plug. The new edition of Southern Astronomer is available. If you visit the website at www.southernastronomer.com, you'll find the necessary information there about how to be subscribed to that particular edition, and it's like I say, the latest edition is out, which is on the screen there. What they refer to as the Special Winter Edition, and yeah, so there it is. Another plug for that. Okay, next on the screen, let's go straight to the first article for tonight, which is an interesting one here. It appears that we have a fairly decent rock from Mars. The largest Mars rocket was up for sale, and I've got a picture of it here. Just bring that up quickly. That's what it looks like. And this is 17th of July. The largest individual Martian rock ever found on Earth has sold at something called Sotheby's. Sotheby's. Never heard of it. It's Sotheby's. Sotheby's. Sotheby's? So maybe it's Sotheby. There's no R in there. Sotheby. Anyway, never heard of it. The largest individual Martian rock ever found on Earth has sold at Sotheby's auction for almost, get this, for almost $5.3 million to an anonymous bidder. $5.3 million for a rock, which supposedly came from Mars. This massive chunk of Mars is a meteorite named NWA 16788, and at 24.67 kilograms or 54.39 pounds, it towers over the previous record holder, a meteorite weighing 14.5 kilograms found in Mali back in 2021. To Tarudini. It was called the Tarudini 002 meteorite. The Sotheby's auction opened on July 16 at 1400 UTC and closed just under 5 hours later. Prior to the event, the value of this scientific marvel was estimated to be between $2 million and $4 million, but ultimately it sold for $5.296 million. The The Martian rock's pristine condition and rich history likely led to its surprising expectations. NWA 16788 shows minimal terrestrial weathering, indicating that its physical and chemical makeup have not been significantly altered since its arrival in the Sahara Desert. Just doing something here. In other words, NWA 16788 is likely a relative newcomer here on Earth, having fallen from outer space rather recently. The rock was likely sent careening into Earth when an asteroid forcibly crashed into its home planet. Based on the presence of a few shock-melted areas and the fact that around a fifth of its makeup is a glass called mascalinite, which forms when feldspar is transformed through intense heat and pressure. The Sotheby's listing states the meteorite was formed from the slow cooling of Martian magma and is characterized by a coarse-grained texture composed primarily of pyroxene, mascalinite, and overline. These microgabaric qualities make it particularly rare. Only 5.4% of Mars meteorites are classified as such. It was discovered by a meteorite hunter in the Agdez region of Niger in November 2023. A small sample was sent to the Shanghai Astronomy Museum, where its Martian identity was confirmed. And there's a close-up image here of the surface of this rock, which is there, which looks interestingly like the Martian surface if you get it on the right angle. But anyway, due to its chemical composition and makeup as described, it is determined that it actually was ejected from the Martian surface from probably some other impactor. As the Martian gravity is much lighter than it is on Earth, the escape velocity for a rock being blasted from the surface is fairly easy to achieve, and that's how they believe that these things end up going into space and eventually making their way to Earth. It's remarkable, but I guess there's some truth in it. But $5.2 million for a Martian rock, I suppose, I don't know, a bit more money than sense in that one. But there you go, people have a lot of money. You're tuned to ASV Radio, VK3 Echo Kilo Hotel, the official station of the Astronomical Society of Victoria. Next article tonight, if I can find it. Oh yes, of course. This is short and sweet, but worth it. Jocelyn Bell, the discoverer of the first radio pulsar. This was published 15th of July because it was Jocelyn's birthday. She was born July 15, 1943. Today, July 15, today in the history of astronomy, the astrophysicist who would discover pulsars is born. And I've got a picky of Jocelyn in here somewhere. There it is. And the story goes, born July 15, 1943, Jocelyn Bell Burnell is a British astrophysicist, best known for her discovery of pulsars. In 1967, when she was a graduate student in radio astronomy at the University of Cambridge, Bell Burnell noticed scruff, in the data she was reviewing from the Mollard Radio Astronomy Observatory. Bell Burnell jokingly called the series a very regular series of regular radio pulses coming from a specific part of the sky, LGM, or Little Green Men. Months later, her advisor Anthony Hewish and their team determined the signals were coming from a rapidly spinning neutron star, and the press dubbed them pulsars. A long career of several universities in the UK followed for Bell Burnell, as did many honours and prizes. Among them, she was president of the Royal Astronomical Society and the Institute of Physics, and received a Royal Medal and the Special Breakthrough Prize in Fundamental Physics. Today, she is a visiting professor of astrophysics at the University of Oxford and Chancellor of the University of Dundee. So that's interesting that the press came up with the term pulsars rather than... I didn't know that, actually. Maybe I did, I forgot that. But the press apparently dubbed the term pulsars, and it stuck. There it is. Well. Anyway, happy birthday, Jocelyn Bell Burnell. And yeah, very good. All right, back to camera one. You're tuned to ASV Radio, VK3 Echo Kilo Hotel, official station of the Astronomical Society of Victoria. Next on the list is an interesting thing. Astronomers discover a perfectly spherical supernova remnant. Published July 14, astronomy.com. And a ghostly near-perfect bubble in space defies expectations about how stars die. And we have an image, so I'll bring that up as well. The Australian Square Kilometre Array Pathfinder telescope captured this radio image of Teleios. So it's a real picture, which you're looking at, radio wavelength. In a universe governed by turbulence and chaos, perfection is really more than a mathematical ideal. Yet astronomers are puzzling over a newfound object that seems to defy that rule. A glowing, nearly flawless circular shell of gas and dust, like the remnant of a long-dead star that has remarkably preserved its shape in a universe where such order is uncommon. Miroslav Filipik, an astronomer at the Western Sydney University in Australia, spotted the remnant while re-examining images captured in May last year by the Evolutionary Map of the Universe survey, which catalogues radio sources across the southern sky using the Australian Square Kilometre Array Pathfinder, or ASCAP, telescope. The newfound remnant, named SNR G305.4-2.2, and estimated to span between 45 to 150 light years, caught Filipik's attention for its exceptional symmetry. He named it Teleios, T-E-L-E-I-O-S, Teleios, which is Greek for perfect or complete. This one was extraordinarily obvious, Phil Popvik recalls. The size of the object and the type of the object, there is nothing even remotely close to it, he says. Although stars begin their lives as almost perfect spheres, Their violent deaths are anything but orderly. In their final moments, a star's core becomes wildly unstable, boiling and sloshing as it implodes under its own gravity. This internal turmoil propels stellar material outward in all directions, but rarely in a uniform way, giving rise to beautiful cosmic wrecks. As the blast wave expands, it's shaped by the complex environment of the interstellar medium, including the galactic magnetic fields, clumps of gas and dust, and scattered debris such as remnants from early stellar explosions rather. These obstacles can sculpt the remnant into the dramatic irregular structures seen in some of the most iconic supernova remnants. They are very rarely perfectly spherical, says Yvette Sendez, a radio astronomer at the University of Oregon who was not involved in the discovery. By contrast, Teleios displays no obvious signs of distortion or deformation that would hint at interaction with denser dust clouds or denser gas clouds, nearby stars or other obstacles. It's quite the little bubble in space, Candace says. It's what you tell your students it should look like if it had a shock wave going out in all directions. In a paper posted to the ARXIV preprint server in May and set to appear in the publications of the Astronomical Society of Australia, Filopovic, I don't know how you pronounce his name, Filopovic and his team suggest that Teleios' near-perfect shape may be due, in large part, to its location at about 2 degrees away from the flat disk-like region of the galaxy where most of the stars, gas and dust are densely packed. In this more isolated neighbourhood, there are fewer stars, clouds and cosmic clutter compared to the crowded galactic plane, a rarefied environment that would allow Teleios' shockwave to expand almost untouched, the new study suggests. That makes perfect sense to me, says Sendez. It's perfectly clean environment. Finally, they say here that Teleios is not just notable for its shape, it's also remarkably faint. Its surface brightness is among the lowest ever recorded for a galactic supernova remnant. Even more puzzling, it appears to glow only in radio wavelengths, remaining elusive across most of the electromagnetic spectrum. No historical supernova has been recorded in that region of the sky, and the object appears absent from older astronomical surveys. Estimates for Teleios' age range widely from less than 1,000 years to over 10,000 years, yet neither extreme fits the characteristics astronomers typically expect for supernova remnants. If it's young, its faintness is puzzling. If it's old, how it has maintained such a perfect, undistorted shape for so long remains a mystery, according to the new study. The more we investigated, the more we were surprised, says Pilpovic. The suspicion here is that we have a special environment which we didn't see before, he says. One possibility is that its surroundings were cleared out millions of years ago by earlier supernova explosion. This prior blast could have swept away most of the gas and dust, leaving behind an almost pristine pocket of space in which Teleios' shockwave could expand almost undisturbed. Another idea the researchers are considering is that Teleios originated from a runaway massive star. Such a star could have been ejected from its birth cluster after its companion exploded, then travelled far and eventually detonated in isolation. there are plenty of runaway stars wandering around, so it's quite possible, Filippovich says. Further observations may detect Teleros beginning to interact with any surrounding material. Current data show a whiff of excess radio emission along the southern eastern edge of the shell, which researchers suspect is due to the interactions with local interstellar medium structures. Such encounters could slow and distort the shockwave, offering valuable clues about the remnant's age, location, and the energy of the original explosion. Additionally, the team is searching for evidence of a so-called zombie star, a surviving remnant left at the centre of the certain types of supernova known as type Ia or 1A explosions. These explosions typically happen in a binary star system where a white dwarf star siphons material from a companion until it reaches a critical mass and detonates, leading to a brief but intense brightening events. While astronomers expect many supernova remnants remain to be discovered, the fact that Teleos was spotted at all is pure luck. Filippovich says, had it been located closer to a galactic plane surrounded by countless stars and clouds, it could have easily have been lost in the noisy backdrop of the Milky Way. It may take another stroke of luck to find a remnant like Teleos. If we are super lucky, we may see another too, he adds. But this type of object, let's put it this way, the chances are against us. So it seems they're pretty lucky they actually found this one in the radio wavelengths. Rather impressed. I do think radio astronomy is quite an amazing tool. Thanks to astronomy.com. VK3EKH, the official station of the Astronomical Society of Victoria, with a regular Friday night cast. Let me just check. Good evening to Andrew, VK3KIS. G'day Cassiopeia. G'day Steve. And g'day Dave, our resident Mount Burnett observer, astronomer, all on the Discord. Watching the HD there. And I'm not really monitoring YouTube, but it looks like it's still working. I upped the power before too, by the way. I noticed that my power level was way down because I was playing AM. So you might have noticed an increase in the SSB signal. Righto. Next on the cards here is, let me just check my email while I'm at it. We have an email from Andrew checking in. We have one from Steve. He says, good signal into Baring. Yep. I have to open up to read the rest of that. 5 9 plus 15. Thanks, Steve. And we have another one here from Dave. Oh, g'day, Dave. Mr. AIF. Listening again as often in the case. Thanks, Dave. Excellent. Good to see you there. And I think you're also able to view the repeater as well, from memory, I think. Which reminds me, just as I think of it right now, the ATV QSO party is scheduled for the end of August. I think it's the 30th. It's only on a Saturday. Usually it spans across a Friday to a Saturday. But yes, I think it's the 30th of August, the ATV QSO party, where it starts at about 10 o'clock in the morning, Saturday morning, and brings in stations from around Australia, and then throughout the late morning, afternoon, crosses to America, and then I believe we're crossing to maybe some UK ATVers as well, probably coming through the like last year's QSO party. We actually had a couple of ATVers patched via the Q So the Q100 geostationary satellite. I think that's right. So anyway, the ATV QSO party is scheduled for the 30th of August. I thought I'd just throw that in there. Righto. You're tuned to ASV Radio. This is your chance to get yourself a set-top box and tune in to the repeater. Information about how to receive VK3 RTV can be found on Amateur Radio Victoria's website. There's a whole dedicated page to VK3 RTV and how to be able to see what set-top boxes work and all that. So yes. Righto, next article, courtesy again of astronomy.com. Why will our sun expel its outer layers as it dies is a question being asked by Daniel Stanya in Kansas. And there's an image associated with this article which I shall, hang on, what's that? There's an email that's just come through it's from Fang. Okay, it's from Fang. And he says 30 dB over 9. Thank you, Mr. Fang. He says audio is poor quality compared with YouTube. Of course, there's absolutely full bandwidth associated with video, with Discord and with YouTube. SSB is only about 3 kilohertz. I can't wait to get my ICOM radio back up and running because the ICOM gave me an extra couple of kilohertz. Although I really should fire up the Anan 8000. The Anan 8000, I can absolutely widen the SSB signal to take up most of 80 metre spectrum. Talk about hi-fi. Anyway, enough of that. I was distracted by Fang. Just in case you don't know who Fang is, that's VK3HK Steve. I can hear him chuckling. Why will our sun expel its outer layers as it dies? Okay, low mass stars like our sun expel their outer layers as a planetary nebula because of what is going on in the star's core as it ages. All right, let me just bring up this picture so you're not always looking at me. Where's this picture? There it is. Okay, so the story, it's a short story. First, let's discriminate between expansion and expulsion. Expansion happens because the thermal pressure from the increased energy production in the star's interior exceeds the gravitational force, keeping the sun's matter close to its core. The sun will expand until a new equilibrium between pressure and gravity is established. This process is ongoing and can continue gradually for billions of years. Expulsion, on the other hand, is a different matter. Massive stars expel their outer layers in a supernova detonation, while low-mass stars like our sun will do so in what is called the planetary nebula phase. The difference has to do with what is going on in the star's core. For billions of years, the sun's core has been fusing hydrogen into helium, which has been settled as an ash deeper into the core region. As the core continues to collapse under its own weight, it heats, that's what I'm trying to say, it heats up the interior of the sun to higher and higher temperatures. The sun adjusts to this increased energy production by slowly expanding in size and luminosity, becoming a red giant star. Eventually, the core's temperature reaches 100 million kelvins, and helium ash begins to fuse into carbon in the triple alpha process, during which 3 helium nuclei fuse into 1 carbon nucleus. If the triple alpha reaction happens in a high mass star, most of the released energy goes into heating the helium ash core, which is a plasma. The massive star expands to another equilibrium size and all is well. However, if it is a low mass star like our Sun, most of the energy goes into heating the core, which by now is made of degenerate white dwarf matter, meaning it cannot be further compressed, nor can it expand to cool off when the temperature increases. When the core is heated in such a star, it begins to once again act like a normal plasma and expands. But some of the energy also goes into heating the Sun's outer layers, which rapidly expand away from the star as a dense stellar wind. This post-red giant phase is usually called the planetary nebula phase and lasts only about 50,000 years or less. In the end, you have the cooling white dwarf core of the star, a powerful source of ultraviolet light, causing the ejected gas to fluoresce as a planetary nebula for a few thousand years. And that example on the screen there, incidentally, this is actually an object in space. It's not some artist's graphic illustration. This is NGC 727, NGC 7027, known as the Jewel Bug Nebula, is an example of a planetary nebula that arises as mass is expelled from an aging star, as will happen to our Sun in the future. So that's an actual object there. Amazing stuff, isn't it? You're tuned to ASV Radio, VK3 Echo Kilo Hotel, the official station of the Astronomical Society of Victoria, with the regular Friday night broadcast. We're coming up to the end. I checked for Tamitha. There's no space weather report from her tonight, but she'll probably release something over the weekend, most likely. Next article, courtesy of space.com. And this is just a quick article talking about our roaming comet that's passing through our system at the moment. A telescope spies rare interstellar comet Atlas, 31 Atlas, zooming through our solar system. And there's a picture here of that. And there it is. And what it says here is that the Gemini North Telescope in Hawaii captured the recently discovered interstellar object called 31 Atlas, revealing a compact coma. The cloud of gas and dust enveloping its icy core. Astronomers unveiled a striking new view of the interstellar visitor 31 Atlas on its journey toward the inner solar system. The Gemini North Telescope in Hawaii captured the newfound comet passing through our cosmic neighbourhood about 290 million miles, or 465 million kilometres from Earth. 31 Atlas was initially detected by ATLAS, which stands for Asteroid Terrestrial Impact Last Alert System, ATLAS, on July 1. It's just the third known interstellar object, meaning it originated outside our solar system, according to a statement from the National Science Foundation, which operates the International Gemini Observatory. There's another image here, which I'll bring up. There it is. The article continues on to say that the sensitivity and scheduling agility of the International Gemini Observatory has provided critical early characterization of the interstellar wanderer, Martin Still, an NSF program director for the International Gemini Observatory, said in a statement, "We look forward to a bounty of new data and insights as this object warms itself on sunlight before continuing its cold, dark journey between the stars." Interstellar objects like 31 Atlas are remnants from distant star systems that have been ejected into space. They offer valuable insights into the building blocks of other planetary systems in the universe, including the chemical elements that were present when they were formed, according to a statement. 31 Atlas is only the third interstellar object detected visiting our solar system after the Oumuamua in 2017, that really long one, and Borisov in 2019. While more objects of this nature are believed to regularly pass through our solar system, they are incredibly difficult to capture. However, at an estimated 20 kilometres in diameter, 31 Atlas is much larger than previous interstellar objects, making it a better target for study. The new images from the Gemini North Telescope show that the comet has a compact coma, the cloud of gas and dust enveloping its icy core. And other observations have suggested that it may be the oldest comet ever discovered, possibly older than our solar system, hailing from the outer thick disk of the Milky Way. In the picture you see on the screen here right now, Comet 31 Atlas streaks across a dense star field in this image captured by the Gemini North Telescope in a spectrograph. The left panel captures the comet's colourful trail. The left panel captures the comet's colourful trail as it moves through the solar system. The image was composed of exposures taken through three filters, shown here as red, green and blue. The right insert zooms in to reveal the comet's compact coma. 31 Atlas will reach its closest approach to the Sun on October 30, passing between 210 million kilometres, or just inside the orbit of Mars. In December, 31 Atlas will pass within about 270 million kilometres of Earth, though it will pose no danger to our planet. Given 31 Atlas's highly eccentric orbit, this will be its one and only visit to our solar system, as its trajectory does not loop back through the Sun or back around the Sun. And that's why astronomers around the world are using a wide variety of telescopes to observe the comet during its brief visit before it returns to interstellar space. It's a visitor coming and going. Righto, you're tuned to ASV Radio, VK3EKH, the official station of the Astronomical Society of Victoria. Regular Friday night broadcast. Where is my camera? There it is. I think we've got one more. Oh yeah, courtesy of sciencealert.com. Record-sized collision between black holes detected by astronomers, July 16. And I might mention too that we are celebrating the launch of Apollo 11 this week. It is currently on its way to the moon. If we cast ourselves back to 1969, this is the very week that everybody was paying attention to that amazing human feat. Two black holes have collided in a merger that could revolutionise our understanding of the black hole growth. And there's an artist's impression of this, which I'll bring up on the picture screen. And two black holes have collided in a merger that could revolutionise our understanding of black hole growth. Named GW GW2, get it right, Clint, named GW231123. You can see why I got tripped over that. It's my dyslexic playing up. Not really. Named GW231123 after the date was recorded on the 23rd November 2023. Truth. It's the most massive black hole collision ever seen yet, resulting in an object heavier than 225 suns. Previously, the most massive black hole collision produced an object 142 times the mass of the Sun. What makes this so incredible is that each of the black holes involved in this collision is heavier than the upper mass limit of black holes formed from single stellar core, suggesting both may have been involved in previous collisions. This is the most massive black hole binary we've observed through gravitational waves, and it presents a real challenge. Real challenge to our understanding of black hole formations, says astronomer and physicist Mark Hannam of Cardiff University in the UK. Black holes, this massive, are forbidden through standard stellar evolution models. Let me just read that sentence again. Black holes this massive, black holes this large are forbidden through standard stellar evolution models. One possibly is that the two black holes in this binary formed through earlier mergers of smaller black holes, they say. Gravitational wave astronomy kicked off in 2015 when the LIGO interferometer detected faint signal from gravitational ripples sent propagating through space-time as two extreme objects merged and became one. Since then, LIGO has been joined by the Virgo and the Kagra facilities, K-A-G-R-A, facilities, resulting or collecting some 300 or so signals from black hole pairs colliding across the universe. 300. Astronomers can analyse and tease apart the signals using the ripples to ascertain the properties of black holes that made them. Here's where it gets really cool. Small black holes are really hard to find in space since they emit no detectable light. By collecting data on mergers, astronomers are collecting data on the reality of black holes. Much of the research around these hypertense objects has been, by necessity, theoretical. We know that the smaller ones, as opposed to the supermassive black holes, millions of suns in mass, are the remains of massive stars that go supernova. Their cores collapsing under gravity to form objects so dense that light cannot escape their gravitational hold. There is, however, an upper limit to the size of black hole this formation mechanism can produce. And there is a little bit of a YouTube video here, which I will run while I finish off this article. Let me just find this YouTube video. Make sure that there's no audio going through. I'll just run it now. Kill the audio. Put it on a loop. All right. Going back to the article. There is, however, an upper limit to the size of black holes this formation mechanism can produce. Because above a certain weight, stars explode in what is called a pair instability supernova that completely obliterates the core. We don't know for sure what that limit is, but it could be as low as 40 or so solar masses and as high as 60. We've already uncovered evidence of black holes that exceed this weight limit. That 142 solar masses merger involved black holes 66 and 85 times the mass of our Sun. But GW231123 ups the ante rather spectacularly. In addition, both of the black holes involved in the event were spinning very fast and very close to the theoretical limit, researchers say. This complicated the signal quite a bit, but it could also be a clue about the history of black holes. When two black holes combine, the resulting single object should have a faster spin rate, a property scientists have proposed as a tool for determining whether a black hole is the product of a previous merger. It's going to take further analysis to unravel all the complexities of GW 231123, but the event could validate scientific theories about how black holes form. It could also be a huge clue about how supermassive black holes grow, since we don't know how they get from objects comparable in masses to a star to the giant behemoths around the entire galaxy's whirl. It will take years for the community to fully unravel the intricate signal pattern and all its implications, says physicist Gregorio Carlio at the University of Birmingham in the UK. Despite the most likely explanation remaining, a black hole merger, more complex scenarios could be the key to deciphering its unexpected features. Exciting times ahead, says physicist Gregorio Carlio. Struth. Righto. Anyway, that's an interesting simulation going on up there on the screen. So it's two black holes merging into one, which causes massive gravitational waves to transcend through space-time. And it's just fortunate that we have a number of gravitational wave detectors now working and detecting gravitational waves all the time. Each time a gravitational wave goes through the Earth, the Earth actually distorts a little bit as a result of that, but we just don't notice it. Just thought I'd mention that. Where's my camera? Bring up the camera again. There she is. Alrighto. Now we're coming up to spaceweather.com. So, where's our sun? Where's this vMix? What's it doing to me? The sun currently looks like this. There's quite a number of sunspots on the sun as we speak. If we could look at the sun right now, safely of course, that's what we would see. And the solar wind is currently at 548.1 kilometres a second. It is blowing a gale. Its density in space is 0.06 protons per cubic centimetre. It's pretty empty. The sunspot number is currently 178. The radio flux, measured at a wavelength of 10.7 centimetres, is currently 156 solar flux units. The aurora over Antarctica looks like this at the moment, and even though it's a fairly significant glow, it's not really producing any auroras that can be seen from the mainland, and quite possibly not really visible from Tasmania, unless you're right down the south coast there, looking in the right spot at the right time. But that's a fairly significant auroral activity over the South Pole, but that's fairly normal too, really. The coronal hole is down in that lower corner at the moment, and from that hole in the sun's corona is where we get a stream of solar wind flowing from this region. The K index, the planetary K index is currently 2, considered quiet, and over the next 24 hours it will go up to 3.67 and also considered relatively quiet. The other report here is that spaceweather.com are advertising the fact that this is an AI-free zone. It's the first time I've seen that. AI isn't all bad. Large language models are good writers with access to vast stores of data. there's still no substitute for a human being with decades of space weather forecasting experience. So this website is 100% human. Backyard astronomy alert. On Friday morning, amateur astronomers can watch the black circular shadow of Titan glide across Saturn. Look for it through backyard telescopes on July 18 between 07 UT and 12:05 UTC. This timing favours observers in the Americas, where Saturn will be halfway up the pre-dawn sky when the shadow appears. It's quite possibly that it has now gone, past and gone. Now, this is an interesting thing that spaceweather.com are talking about here. Have a good listen to this for a moment. Let me just bring up this image associated with this article. Moths follow the Milky Way. Astronomers come in all shapes and sizes, even invertebrates. A new study published in Nature reveals that Australian moths can see and decipher the night sky. They pay particular attention to the Milky Way and seem capable of navigating using the Carina Nebula as a visual landmark. A male bogon moth and a diagram of their annual migration on the screen there. Every spring in Southeast Australia, billions of bogon moths take flight under the cover of darkness. It's the beginning of an epic migration as much as 1,000 kilometres long. Their destination, a small cluster of caves in the Australian Alps, places the moths have never visited before, yet somehow navigate to with remarkable precision. Their compass, it turns out, is the night sky itself. Reaching this conclusion required the researchers to do something you probably don't want to think about too closely. They attached the moths to tiny little tethers. Moths could lift off and pick a direction, but not escape. The experiment unfolded inside a special moth planetarium. Star patterns were projected. Star patterns were. The things these people get up to. The star patterns were projected onto an overhead screen, while the ambient magnetic field was nulled by Helmholtz coils, guaranteeing that the participants could not cheat using magnetic navigation. Helmholtz coils. Okay. When shown a normal star field, the moths orientated in the correct direction, but when the stars were scrambled into random patterns, they lost their bearings. To dig deeper. I'm getting tired. To dig deeper, researchers recorded activity from visual neurons in the moths' brains as projected night sky rotated overhead. Neurons fired most strongly when the stars aligned with the moth's inherited migratory heading. Some neurons were turned into the brightest region of the Milky Way, especially near the Carina Nebula, suggesting that this band of starlight is a visual landmark. Clouds produced the next revelation. Bogon moths remained orientated even when the stars were hidden. In most cases, they relied on Earth's magnetic field instead, revealing a dual compass system similar to that of migratory birds, full stop. When both stellar and magnetic cues were removed, the moths became disorientated again. In recent years, scientists have discovered that many creatures are guided by the stars. In addition to humans, the list includes migratory songbirds, possibly seals, dung beetles, cricket frogs, and now bogon moths. The list of life forms guided by magnetism is even longer, ranging in size from microbes to whales. Fascinating. As of July 18, 2025, there were 2,349 potentially hazardous asteroids, but none of those asteroids are on a collision course with Earth. There it is. That's this week, this day, spaceweather.com. You can read it for yourself. Amazing stuff. I am really looking forward to the magnetic poles flipping to see what that does to the scheme of things on this planet. It's about time it does. All right, that's it. We've come to the end of tonight's session at 6 minutes past the hour, 5 minutes. It's amazing how that hour is still filled up. It always amazes me. And the streams have hung in there. I'm still on Discord. No, don't stop it. I almost pressed the wrong button. So let me just quickly check Discord. We still have the usual folks watching there. And I can't check YouTube because I'm not really monitoring it. Just a quick check of email. Nothing new there. All right, that's fine. On that note, we shall now go across to 80 metres. Because I start intermittently broadcasting on 80, that might upset the YouTube stream. So if I do disappear on the streams, my apologies in advance. But let's hope I don't lose the streams, the Ghostbuster streams. You can't cross the streams. It would be bad. Oh dear. No, it's all right. Something else I was just thinking of. This is VK3EKH, listening on 3541 kilohertz for any stations wishing to check in.
Kilowatt 3 Delta X-ray. Yeah, don't cross the streams there, please. VK3 SPX.
All right. VK3 Delta X-ray and VK3 SPX. Anybody else? The list is getting shorter every Friday. Oh dear. Have a say, Greg. VK3 Delta X-ray. Good evening to you, VK3 EKH.
Yeah, good on you, Clint. Thanks for running the net there tonight and the broadcast. Yeah, excellent. And very interesting in those photon moths. We used to see them down here a little bit, but can't recall seeing them for a few years now. So yeah, maybe they've cut their journey short. There's a nature of a terrific thing when you think about it, how they, they're smarter than we are there, Clint, I'm thinking, for sure. Anyway, good broadcast, signal 20, 30 over, terrific signal. Isn't it that spike tonight there, Clint? So the audio might be a little bit better. I've had a few complaints there from the bowl shop net. I bought out the A2 desk mic, so hopefully it sounded a bit better there, Clint. Sounded like I had too much space. Yeah, Sam just broke in on, I'm not sure what he broke in on channel 50, but he sounded good. Thanks, Sam. I know he's listening on Discord. Back over to you there, Clint, and thanks for running up there, mate. I'll be around there next week, I hope. So, cheers, and back over to you, Clint. VK3EKH. VK3 Delta X-ray, Greg and Audible.
Yeah, good on you, Greg. VK3 Delta X-ray, Warrnambool. VK3 EKH. Yes, you're sounding perfectly well, Greg. Good signal from you. You're 30 over 9 here tonight, and propagation is good on the band, and sounding okay to me through my external speaker on the 9000D. So not a problem there with that microphone. And I'm not 100% sure about my own audio tonight, but I think it's doing okay. Anyway, I haven't had any complaints, generally. All right, thanks, Greg. And we'll be here next Friday again, doing it all again. All right, across to you there, Steve. VK3 SPX, VK3 EKH.
VK3 EKH. HVK3SPX. Yeah, nothing wrong with your audio, Clint, except it not being as good as Discord, of course. So, see about that. Not surprising. And Greg, your audio is better than it was the bowl shot net, I think, as well, too. Anyway, that'll do it for single reports. Yeah, that spherical supernova remnant, that was pretty amazing, wasn't it? I'm really gobsmacked that you can get such a crisp-looking image. It looks like an image for an optical telescope, and that from a radio telescope. So I don't really have a good understanding of how you get such a really good image at radio wavelength. I know how optical telescope works, but I don't quite know how you form an image so well with a radio telescope, and I'm sure you do know that, Clint, so maybe you can tell us. And the bogon moth, well, that's pretty amazing, isn't it? I know I wrote a bit of an article about light pollution for our little Barring Up newsletter, and just about a month ago. And certainly one of the problems is that those bogon moths are put off track by artificial lights that are very bright in some cases around the countryside, particularly with chicken prisons, as my wife calls them, and they can get basically lost. And then the pigeons puzzle to actually feed on the bogon moth. They starve as well, and everything goes from bad to worse. But amazing that they can find such a small site guided by the stars. That's pretty mind-boggling. Anyway, yes, mind-boggling is what astronomy is all about, isn't it? All right, thanks, Clint. We'll see you next time. VK3EKH, VK3SPX.
Yeah, I agree, and I love the way they did this simulation, more or less, by getting the moths into a planetarium where they could they could simulate the sky from the planetarium, and then attaching what was it, some sort of tether to the moths, and being able to, more or less prove that with the stars in a random configuration, they were disorientated. But as soon as the stars were configured in the proper pattern, and particularly showing Carina, they were able to fly accordingly in the right direction. It's it is amazing, and it is intriguing that the Earth's magnetic field also plays a part in all this. So, it's really an amazing thing, life here on Earth. And the radio image there, I don't know exactly what wavelength it was, all that data was collected. Suffice to say that every object that you see in that image is a radio object. They're not just not stars from an optical point of view, but every object there, every bright source would be probably some sort of a radio galaxy or an intense radio source. And of course, when objects like, again, I don't know how many arc seconds or milli-arc seconds this image would be across, but it's a combination of they're using the Australian ASCAP, which is multiple radio telescopes, all scanning that part of the sky. And as the telescope scans that part of the sky, it picks up the varying differences or intensities in radio signal, and that increase in radio signal in the temperature of that part of the sky is ultimately an image is produced. So this image, even though it can't be seen in the optical wavelength, in the optical spectrum, it's certainly being detected in the radio spectrum. I'd be interested to know what wavelength they were using to actually to see this object. I'll do a little bit of research into that. I'll look up the ASCAP file and see if I can find out what band of frequencies were used to collect that image. But essentially what you're seeing there is all radio, bright sources in distant galaxies, radio galaxies, and of course the brightest areas, they're producing that particular spherical image. So yeah, I'll see if I can find out some more information on that. It really is quite fascinating. It's just amazing what radio astronomers are able to do with their instruments. All right, now just a quick show and tell. This arrived today. The dew shield for the Celestron telescope. So this is the aluminium one, the aluminium tube. You wouldn't think it would cost too much, but being Celestron, of course, there was a few dollars attached with this. Anything, honestly, anything to do with telescopes, it's just a minefield with the cost of things. But anyway, that's the dew shield. It's to try and prevent dew from forming on the front of the telescope. It's got the cable ducting. You can just see there. So if I'm running a camera on the front of the telescope, that's where you can run the cables through. Anyway, that arrived today. So I'll fit that to the front of the telescope probably this weekend. I'm still waiting for the temperature, the element, the heating element, to put around the telescope. So for some reason it's just taking an awfully long time to come through, and the same also for the pier. I don't know why it's taking so long for Sidereal Trading to get the pier and the adapter plate, because as soon as I get those, I'll be able to mount the EQ6 Pro equatorial motor drive, and hence mount the telescope. So it's really awkward to do anything at the moment manually. It's like putting up your beams and directional antennas and doing Armstrong method, and like, where's the signal? You're turning the beam for maximum signal, and your radio's in the shack, and you can't peak the signal because it's the radio and the antennas are outside. So you've got to have a rotator. When you're doing ham radio, you've got to have an antenna rotator, and if you're doing satellite work, you've got to have a rotator that's azimuth and elevation. So certainly the same deal with astronomy. You can set up a telescope out in the field, and you can manually turn the telescope around if you know what part of the sky to go to quickly, but that comes from experience. So I've already tried doing that at 4 o'clock on a Sunday morning, manually turning that telescope at the same time, turning the dome so that the shutter was in the right part of the sky. But I had no idea where I was looking, and I'm inexperienced at choosing the right eyepieces at the moment. So I actually found it easy to use a pair of binoculars to look at the sky. In fact, there was an object I could see through the binoculars. There was a little fuzzy patch through the binoculars. I could always point the binoculars. There it is, and I'd take the binoculars away and I'd be looking by eye, and I think, I can't really make it out by eye, but there is something there. But do you think I could get the Celestron to point at it? Oh, struth. And the more I tried to get the Celestron to see this object, the colder things were getting. The amount of dew on the front of the telescope was, within 4 or 5 minutes it would come back, and it was just time to give it up for the morning. Went inside. So I am still waiting for my pier, and so I can mount the telescope, get the computer control system operating 100%. So I can tell the computer to find that object for me, and there it is, and I can then look and be blown away by the objects. The first globular cluster I ever saw, I can't remember which one it was, but I This was years ago before I became a member of. I might have been involved with ASV, but at the time, the Melbourne Astronomical Society, which was run by somebody by the name of Chris Ellis, he was conducting astronomy classes, and they had a dark sky site down in South Gippsland somewhere, and a part of the astronomy course was to go down to this footy oval in Gippsland somewhere, and they had all these telescopes set up, and the thing that I remember about that particular night was the ground was really cold, and I was wearing runners, and the cold from the ground was coming straight through the shoes. So, I learned very quickly that if you're going to be out in the field with your telescope at night time, you've got to be really, really rugged up and wear thick-soled shoes, or else you'll end up with cold feet, which is not a comfortable thing. But I looked through a Cassegrain telescope. I can't remember what brand it was, but the astronomer had had set up the telescope on a globular cluster. And to this day, right now, in my mind, that globular cluster is burned into my brain cells, and I could not believe it was a full image. It took up the whole view of the screen, and you could almost count every star that was making up that globular cluster. It was so bright, and there was thousands and thousands of these stars, a globular cluster, and I haven't seen it since. So I'm looking forward to seeing this globular cluster in my own observatory in the near future. But it's such a beautiful object, it really is. And to think that if you had a starship like the Enterprise and you flew towards this star cluster, that you would probably be able to safely navigate right through that cluster of stars without any chance of impact or crashing into a star, because the stars in a globular cluster are still separated by millions of kilometres. It's almost as if there's a core to it, and they're really all very close. But apparently they're not. That's not the case at all, from something I read some time ago. Anyway, enough of that rubbish. All right. Anyway, there's my dew shield. So, like I say, I'm still waiting for the pier to arrive, and patience is a virtue, as they say. All right. On that note, I'll pop back to you quickly. VK3SBX, VK3 EKH.
Yeah, VK3 EKH, VK3SBX. Yeah, that looks great, Clint. I've got a dew shield, but it's not the metal one. It's thick plastic sort of thing, which does have some advantages, but I think you've got a better deal there. So that looks really great. Yeah, so I hope you get all that up going soon. You were sort of going from manipulating the telescope by hand to computer control. I actually think I went through about 3 or 4 steps on the way from, manually trying to point it in the right direction to getting the computer to plug it direct off the object to the nearest arc second. So there are some in-between methods which you may or may not care to examine on the way there.
Yeah.
You really should come for a visit one day, actually. Let me show you a few things up here, the way I've got it all set up. Anyway, yeah, good luck with that, Clint. Yes, very good. It's expensive. It's exactly the same ham radio. You buy one thing and there's always something else to buy. So it's just the way it is. All right, thanks for CK2 UKH, CK2SPX.
Yeah, thanks, Steve. Yeah, no, totally. I think the things that I'm going to be exploring very soon too are cameras. I want at least 2 cameras, the planetary and deep sky camera. I'm still trying to make up my mind which is the best one to go. I'm looking at Eddie Pang imagery that he's doing, and he always indicates the cameras that he uses. So yeah, I'm looking at the kind of cameras to get, and also I need to understand eyepieces, the correct kind of eyepieces to use. I've got some eyepieces here, but I need to get a bit of a feel for what eyepieces to use to be able to widen the view of the sky, understand how Barlow's work and how reducers work, and just get a bit of a feel for all that. So it's coming, and yeah, no, I agree with you. If you ever speak to Perry Vlahos, who is very, very knowledgeable on the night sky. He's quite an advocate for being able to bring out your telescope into the field, like a Dobson telescope, and use a star map, just a paper map, and above your head there. That's what the sky should roughly look like, and let's swing the telescope in that area. But you've got to start off with an eyepiece that's wide field, so that you can get the telescope in the right position, and then you can choose the right magnification piece to zoom in a little bit on the object of interest. Of course, the image darkens a little bit, but and of course that's where astrophotography is going to be really good, because you can just expose these images to get the right lighting. Anyway, we'll get there. I just hope that being in this area of Narre Warren, because there's a bit of light glare that we're having to deal with, but I've seen plenty of decent images taken of deep sky objects from suburbia, and it is possible to filter out a lot of the haze and the light from street lamps and stuff like that, yet to be discovered. Anyway, all right, what's the time? It is 11:30. So I shall continue on from this point. I won't drop off right now. Well, I'll finish up on 80 metres, but I'll continue with the streams and the RTV transmission. And what I'll do is I'll run last Wednesday's Astro Talk, which is just in here somewhere. I think that's it there. Which was where are we? Which was like I say, last Wednesday, 16th of July, and it presented Sarah Caddy, which is exploring the rapidly growing challenges of space domain and awareness. As more satellites launched this decade than all human history combined, the need to track, identify and monitor space objects is more urgent than ever, both for astronomers dealing with light pollution from satellite trails and for protecting critical infrastructures like GPS, communications and disaster response systems. Sarah will outline the cutting-edge work being done by University of Melbourne, Macquarie University, to tackle this issue. So I'll run that YouTube feed, courtesy of the ASV, in just a second. I'll just queue it up. Oh, it's already queued up. Okay. So I shall cease transmissions on 80 metres. If you wish to watch this YouTube talk, it only goes for about 40 minutes, the actual talk by Sarah. So it's not very long, but I suspect it will be a very interesting talk. So it'll be introduced by the ASV president, Mark Ascario, the one with the colour hair, and and we'll give that a airing right now. So thanks everybody for coming up on the callback, for those that did, and we'll be back next Friday here on 3541 kilohertz to do it all again. So we'll conclude on 80 metres, but we'll run this video on the Discord and YouTube stream, as well as via Melbourne TV repeater. This has been VK3EKH, the official station of the Astronomical Society of Victoria, with the regular Friday night broadcasts concluding on 3541 kilohertz. Cheers everyone, have a lovely weekend, and we'll see you next Friday. All right. Okay, let's segue into our stream, into our YouTube thingy, and see how she goes. In fact, before I do that, I better make sure that the audio is going to work on Discord, and that should do it. Yep, that should do it. All right, stand by for the program.
Good evening, everybody. Welcome to July's Astro Talk. I guess the first question I've got to ask is, are you afraid of spiders? Because tonight it's all about a telescope named after the Huntsman Telescope, and we're going to hear all about it from Sarah Caddy. And Sarah is a PhD candidate at Macquarie University studying the challenges of detecting the light from the first stars of the galaxy in our universe from low Earth orbit with Hubble Space Telescope and the upcoming Australian Skyhopper Space Telescope. Sarah also works with the Huntsman Telescope team deploying edge computing devices that enable sub-second imaging of fast transit sources for the Huntsman Rapid Transients and Optical Repeaters Survey, RAPTORS, and has a keen interest in science communication and education, celestial navigation, space science, and technology. And I need to thank Kelly Clitheroe for getting Sarah to come along and give us this talk. A quick reminder, tickets to Vastrock are currently available. Links to the event can be found on the AAC website under Events tab. It is down in Geelong this year at Eden Oaks, and there is accommodation available on site as well. Following Sarah's talk, we have the real Bill Stent, the telescope gent. The fake one is not here tonight. The real one is here, and he will be sharing with us what's in the sky for June and July. But without further ado, let's bring Sarah in. Good evening, Sarah. How are you going?
Hi, not too bad. Great to be here.
That's all right. I'm going to hand straight over to you, Sarah, and let you get stuck into your talk and tell us all about the Huntsman Telescope project.
Okie doke. Can you see full screen there now?
We can, yes. Go for it. Floor is yours.
Okay, so thank you again for having me. I'm going to be talking about the Huntsman Telescope project today. The blurb might have been a little bit out of date. I am a research fellow at the University of Melbourne now, so I'm a Melbourneite. And I'm actually working on something different. I'm looking at space domain awareness, so tracking, monitoring, and characterizing satellites. So I'll talk a little bit about that as well in this project, because Huntsman was actually the precursor to that. But tonight I want to talk about a little bit of lessons learned from living on the edge of what's possible with off-the-shelf technology. Huntsman has been in my life for about 10 years now. I still absolutely love it, and it sort of live and breathe the telescope. And I love giving a Huntsman talk because there's something special about it for some reason. People really connect with Huntsman. Unlike, the VLT, large, big telescopes that take governments and huge organizations to make them run, and they seem so unfathomable and untouchable. Huntsman is built from components that you can buy online, components that you probably, or some of you may already have. And despite it being made from very unassuming components, it can still do some pretty incredible science. And so every time I've spoken to people about Huntsman, every time people have met Huntsman, they always get excited about it. And it's one of the really magical things about this telescope. So what I'll explore tonight is a little bit about who I am and what I do. an introduction to the Huntsman project and some lessons learned from building the telescope. It's been a long journey, but we're finally sort of there at the end and seeing the fruits of our labours now. Get down to details, some of the science cases that Huntsman is looking at, and also a little bit of the outreach that we do as well. So first of all, who am I and what I do? Well, when I'm not observing with or debugging Huntsman, which was a huge amount of what I did as a PhD student, what I now do is I work with this instrument here. This is called Spirit. It's a satellite in orbit. It's been there for about 2 years now, and it's operated by the University of Melbourne. And Spirit is actually a little space telescope. It has an optical and infrared telescope on board, as well as a gamma ray detector. So what Spirit is doing is it's actually surveying the entire sky, looking for these really intense emissions from things like the collision of black holes and supernova events. And it's actually hosting an instrument on board from the Italian Space Agency, which it uses to do this. So I've moved from using telescopes on the ground to telescopes in space now, which is a whole different challenge. And I actually ended up taking a picture of my telescope on the ground at Siding Spring Observatory with my telescope in space, which was a pretty cool moment. And another big part of what I do is dealing with this problem that we have of pollution in space. So we've got this problem where, just like we pollute, unfortunately, the oceans on Earth, and we sort of think of these spaces as out of sight, out of mind, and put rubbish and trash up there. We do the same thing with basically the space around us. And we're also dealing with this new phenomenon of satellite mega constellations, which are clogging up the skies. And I'm sure many of you as astrophotographers and astronomers would know these satellites get in our images, and this problem is becoming larger and larger. Not only that, but the space debris runs into other satellites, and then you get breakup events and you have a sort of runaway situation. And so as an astronomer, I feel a lot of, custodianship of the sky and wanting to preserve it and keep it dark and quiet for everyone. And I'm trying to find ways of working with satellite operators so that I can help them by tracking and monitoring their satellites. And in the same way, they can help us by reducing the brightness of these satellites so that we don't have to worry about them impacting astronomy anymore. So a bit of an introduction to the Huntsman project and how all of this started. So Huntsman is located in the Warrumbungles Dark Sky Park. If you've never been there before, it's about a 12-hour journey from Melbourne. It's a long way. And yes, I've done that a few times when things go wrong and I have to fix it. About a 6-hour drive from Sydney. And it's this absolutely incredible place. Some of the darkest skies in Australia. But as you come up to it, you're sort of driving along this complete plains expanse for as far as the eye can see, and then all of a sudden you see these huge pinnacles coming out of the ground. And they're actually the remnants of sort of plugs from this ancient volcano that used to be there. And it's just one of the most magical places I've ever been, and I really love going back there every time. And Huntsman sits perched on top of one of these at a place called Siding Spring Observatory, and has the most incredible view. And if you're interested in coming meeting Huntsman, we have this thing called Starfest, which is held at the October long weekend every year. I always call it Astronomer's Christmas. I get the same feeling the night before Starfest as I do Christmas. And we open the site to the public. It only happens one time a year. And we have about 3,000 people come through and see the largest optical telescope in Australia, every other telescope that is available in the mountain. And of course, we open Huntsman as well. So a fantastic event if you want to come along and have a look at some of the optical facilities that Australia has to offer. But on to Huntsman. So it's a 10-year project and counting, and I had to update that number today. I can't believe it's been 10 years. And the one original goal of Huntsman was to build a fully autonomous robotic telescope designed to look for low surface brightness objects in the universe. So we're talking about the outer edges of galaxies, this fluffy, diffuse stuff that tells us a little bit about how the universe and how galaxies were formed. And Huntsman is really well designed for this. It uses lenses, and for those people who have refracting telescopes instead of reflectors, you'll know that the PSF, or the way that the light falls in your camera, it is very constrained to one point when you look through a refractor as compared to a reflector when the light gets pushed out into these very characteristic little star-shaped points. And that helps you accurately measure the brightness of these objects. And I can tell you when the first images from LSST or Vera Rubin Observatory came out just a couple of days ago, I think this image in particular got me extremely excited, and I was absolutely in hysterics because there was so much information to take in one image. But I thought, oh my goodness, where is the world now for telescopes like Huntsman? What can we contribute to? But if you have a look closely at this image, you'll find that you can see the stars have these very characteristic point shapes around them, and the light from these big bright stars impacts these faint diffuse structures around the galaxies. And that's where telescopes like Huntsman come in. So we can constrain that light to pinpoints around the stars, and we don't have to worry about it contaminating other parts of the galaxy. And what's fantastic is that LSST can go off and look at all of these galaxies and look at all of this stuff and tell Huntsman what it's really interested in and what we want to look at more closely. So Huntsman isn't by itself. It was inspired by another telescope called Dragonfly, located in the Northern Hemisphere. And this huge instrument has 48 lenses on 2 arrays. I think they're almost up to 100 lenses now in total. It's a huge project. And what they're doing is looking for dwarf galaxies. So these funny, fuzzy little blobs that almost don't look like anything, but these very diffuse galaxies that tell us a little bit about how the universe was formed. So why Huntsman? It's a strange name for a telescope. Well, it's named after, of course, the Australian huntsman spider. And because Huntsman has lots of eyes, it looks a little bit like the telescope itself. It's also a regular visitor to our dome, and I can tell you it's a terrible night when the Huntsmans decide to scuttle across your keyboard when you're sitting there. But it's still, yeah, it's pretty cool. We've sort of come to love little Huntsmans in our dome. So a brief overview of Huntsman. It is a telephoto array. There's 10 lenses. They're all looking at the same patch of sky. 10 lenses, 10 times the amount of photons. So we can reach surface brightness limits of around 13 mags per arc second in only a few months of observations for a target. And of course, why lenses? Well, they're tailored to the low surface brightness science case. We're looking for excellent stray light control, and that's something that only a refracting telescope can really give you. Getting into some more of the details, and of course I put this telescope together with my hands, so if you want to ask me about anything, please go ahead. But we have sort of dew heat controls, thermostats for temperature regulation, camera power distribution boxes, everything you'd expect on a regular telescope, except we've got 10 of them all together. The lenses themselves are Canon 400mm f2.8 lenses with a diameter of about 14 centimeters. We've got these 2 network switches on the back, which feed 10 NVIDIA Jetson Xaviers, and these are sort of edge compute modules, little fancy computers, and these allow us to process data in real time as they come off lenses themselves. Otherwise, you can imagine having, especially if you're looking at exoplanets or if you're looking at fast things, you've got 10 cameras all firing at once. That's gigabytes of data coming off your telescope. So it's really good to be able to process that and decide what you actually want to keep when it comes off the telescope. It's got about 1.9 by 1.3 degree field of view, so it's fairly large. And we do use the software BISC ME2 mounts with the SkyX. We have a solar-powered dome, which causes a lot of trouble, and I'll talk about that later as well. And around 20 megapixel cameras. We use the ZWO ASI 183s. We upgraded from SBIGs a while ago. And unfortunately, the ZWOs have been incredibly unreliable, and I'd be interested to hear if other people have had experiences with those before. And we have 7 slot filter wheels with Sloan GNR and HR for an S2, as well as a dark and a luminance, just for fun. So what makes a robotic telescope tick? And this was probably the most challenging part of the project. So Huntsman is not just a telescope, but it's also a robot. And if you think of all of the things that you do as an astronomer, when you go out to take an image of the sky, these are all things that a telescope has to do by itself. So it has to think, it has to have be able to sense its environment, it has to make decisions for itself based on what it's experienced before. And this is pretty much what took the 10 years of trying to design a system that would do this efficiently. So things like a weather system, dome control, doing calibration fields at the start and end of the night, scheduling what you want to observe next, target acquisition and tracking, making sure you're tracking correctly. Things like data management, how much data is coming off the telescope, where do I need to put that after I've taken it? Coordinating 10 different cameras and focusing all of those 10 different cameras at the same time. And of course, the usual things like startup and pack down. So there's a lot of things that you do as an astronomer that we sort of don't think about. We just do them because we know how to do them. And these are things that Huntsman sort of had to learn in a way to do by itself. So everything that you need to run a remote observatory is all freely available online. If you're interested in building your own Huntsman, or if you just want to automate your own observatory, there's something called Huntsman POX, and that is the observatory control system for Huntsman. And with essentially 3 lines of Python code, if you're Python savvy, you can essentially run your robot observatory just from there. Huntsman has its own weather system, of course. As I mentioned, it has to sense its own environment. It measures the ambient temperature, the wind speed, the sky temperature, all of those usual things that you do as an observer, with a custom software suite that allows us to interact with it and check up on it and see how it's doing. It also interacts with all the other telescopes on the mountain. Because they're so far apart, it can ask the AAT, hey, have you detected any rain yet? Can I expect that in the next couple of minutes? And it talks to the other telescopes to make sure it's on the right track and it's doing what it's supposed to be doing. It also has webcams, one on the outside and one on the inside, so that we can check up on it and make sure that the dome isn't open when it's raining and things like that. One of the hardest parts has been letting it go and just letting it do its own thing and not constantly monitoring it at night. So lessons learned from building a robotic telescope, well, some of them might surprise you. The first one, that it's very difficult to control the weather, and in particular, it's difficult to protect it from lightning. We found that especially when you're on a mountain, which has a reputation for a lot of lightning strikes, in fact, we get about 4 direct strikes per year, it can be very difficult to look after your telescope. This is a picture just taken of a storm when I was on the mountain one night, and earlier in the morning, we found that strike was just close to the telescope of a tree there. And unfortunately, Huntsman's been hit by lightning twice, and what tends to happen is the lightning hits the area near the telescope, and because of how the structure underneath it is built, all these sort of metal pipes and things, the lightning runs up, the electricity runs up through there, and we've had to replace all of our control electronics at least once because of all of these lightning strikes that we get. So it was humble beginnings back in 2015. The first sort of part of the project was checking to see whether or not the concept worked. This was still early days for Dragonfly as well, so trying to work out the best way to put a telescope together. And of course, it was just one lens in a shed, still in the Warrumbungles though, beautiful dark sky, but still, yeah, humble beginnings for the project. We started to build up from this, just an example of tarantula we took a while ago, and start to mount the Huntsman lenses on other telescopes. This was at Macquarie Observatory, and we spent a long time on the top of these telescopes, eventually building up the array larger and larger and trying to learn how to coordinate all of these different lenses at the same time and building the software to be able to do this. Lesson 2, it's difficult to keep a fiberglass dome perfectly spherical. This is a problem that's been continuously getting worse as we go along. And I don't know if anyone else has had experience with fiberglass domes before. I know I've spoken to a few people in different astronomical societies around Australia who have said the same thing. You end up getting strong winds and it flexes, and the how spherical the dome is changes, and eventually, because it's rotating around, it starts to pull itself apart. So I like to bring up these lessons learned because I essentially learn from you guys and try and understand people who have years and years of experience with these sort of projects, what you do to try and keep your telescopes functioning for a long time. So just another perspective shot here of Huntsman during commissioning phase, taking a picture of it sitting back from the AAT, the big telescope on the mountain. It sits up there barely exposed on the top of the mountain by itself. And this is what it looked like back in the early days. We had 5 lenses on the bottom, and we had a big Roerich-Schmidt astrograph, which we were using to try and work out if it really was an appreciable difference between using a lens and using a reflecting telescope. And we found that, of course, the PSF, the point spread function, the light that was getting scattered in the image was drastically reduced with a lens-based system. And of course, we were very excited when the telescope was eventually commissioned, at least in its early stages. Lesson 3, and I hope this doesn't trigger too many people, no matter how many times you tidy your cables, you'll never be satisfied. Sometimes I go up there and I just have to spend a cathartic moment just tidying the cables, because as you add new things to the telescope, as you change things, as you're changing the configuration, it gets messy, and then you have to go back to the drawing board and tidy it all up again. Yeah, it's an ongoing process that evolves. One of the first things we actually observed with the telescope, and this is quite funny, is in 2018, we had a look at Starman. So when Elon Musk decided to shoot one of his Tesla Roadsters into space and send it to Mars and ultimately lose it, we thought, wouldn't it be funny if we could find it? So on one of the nights, immediately after the launch, we were monitoring Elon Musk's Twitter, back then when it was called Twitter, and just trying to work out, he was posting sort of rough coordinates of where it was. So we were sitting there scanning the sky trying to find it, and eventually we did. It's just funny, this is one of the first things that we saw with Huntsman. The fourth lesson is that ants love electricity. This wasn't something I ever thought I'd have to deal with as an astronomer. It never occurred to me that I'd have to be proficient in pest control. But unfortunately, when you are building an observatory out in a remote location, this is one of the things you have to deal with. Every time before it rains, for some reason the ants come. They like to build bridges over electrical contacts and short circuit a lot of the power control systems that we have. And on top of the ants, we also have rats. So when the drought started to break just a little while ago, we had this large population of rats move in, which started to eat everything from the camera boxes and things we'd left up there to all of the electronics, all of the cabling underneath the floor of the dome, which all had to be replaced because they like to chew it, which was something, again, completely unexpected. So there's been a lot of setbacks in this project. Lesson 6, when you use anything in developer mode, it will start to fail. And my viewpoint is always to use duct tape to patch up big problems. And the image in the background you're seeing here is actually coming as is an image from one of the ZWO cameras. So we are using them in a bit of an unconventional way. We're not using the software that's provided with them. We're using our own Python scripts. And we do use them quite rigorously. So they're being used every night, and as we'll see as well during the day too. And they run continuously for a long time. So they do fail quite often. We send them away to ZWO and they send them back and magically they've been repaired. I'd be interested to see if anyone else has seen something similar to this in their time using them. Another lesson learned is that Raspberry Pis are great until you need to process images. So back in the early days, and in this image here, when we were doing some of our first tests with Huntsman, before we were actually running proper observing runs, the Raspberry Pis were fine, but they only have a little bit of RAM. So when you're actually starting to process images on board, you need something a little bit more powerful. So we ended up replacing all 10 of the Raspberry Pis with NVIDIA Jetsons. Now, this was also presented a problem because we went with an interesting company that were just sort of getting started. And if a small company is claiming their product can do amazing things and move mountains, it's probably too good to be true. Unfortunately, we had a lot of trouble with thermal control with the Jetsons. They would overheat. So it's just been a constant process of learning lessons and getting to where we want to be. Lesson 9, and probably one of the biggest lessons learned, was trying to replicate an astronomer's judgment and workflow in software is hard. Again, like I said, this is one of the most challenging parts of the project. Although the hardware, and I enjoy working with the hardware, you just put it together and then it works eventually. But the software is more challenging, and trying to replicate that intuition that an astronomer has is really challenging. And lesson 10, Australia is a pretty wild place for a remote observatory. This is a video that I took a couple of years ago before the drought broke, and this was before a storm, but the clouds that you're seeing rolling in there is actually a dust storm. So we used to get these quite frequently, and this is just a cloud of red dust, and what it would do is it would just sort of come and get into everything. Even if the dome was closed, it would still settle all over the telescope. So you'd have to go up every couple of months, clear all the red dust off your telescope, which you can imagine is not good for low surface brightness imaging, and then start again, and then of course the dust would come and settle again. And lesson 11, it's really wild, the weather. So we go from these crazy droughts and really hot conditions, 40-degree days, to sometimes it snows on the mountain. So it is pretty crazy. But eventually, after all of that, just a couple of years ago, we exited commissioning phase and back into more traditional observing, which was really exciting to do. This is one of the first nights where we started to do proper observations. So final lessons learned is things never, ever go to plan, and so plan for that. I think that's probably one of the most important lessons I've learned from Huntsman, was how to manage a project and how to plan for the unexpected. Always test your subsystems before deploying them so that you know what's going on. Test your entire system in an environment you can control before you go out there. And I'm sure many of you do, particularly astrophotographers. You have to test all of your hardware before you go out there and try and take that money shot. So hold your telescope's hand before you let it walk on its own. One of the hardest lessons I had to learn was let Huntsman do its thing and trust that it wasn't going to open the dome when it was raining. And what can happen will happen. I think that's a lesson learned for every project that we do. So let's get down to the details. Let's talk about the science. So there are a couple of things that we're interested in with Huntsman, not just low surface brightness imaging. The project has really expanded out to be all sorts of things as different people come onto the team and want to explore different things, which I think is absolutely fantastic about the instrument, that it's so versatile. So the first thing is fast transients. So these are things like fast radio bursts. These are intense bursts of radio emission. They come from all parts of the sky, but we're not entirely sure where they come from yet, which is really crazy. We see so many of these radio bursts, and we don't know where they're coming from. So what we want to do is look for optical counterparts to those to try and pin down where they come from. Another thing are flare stars, essentially stars that are really active and they're sending out these coronal mass ejections, but on huge scales, much larger than the sun. And we want to try and understand this. Does this have implications for planets that would be orbiting around that star? And what does that mean for the habitability of those planets? We're also interested in gravitational wave progenitors, so looking at the optical counterpart to these events. And of course, space situational awareness, which is where sort of my interest comes in. And then working with other programs like Deeper, Wider, Faster, and other instruments like DREAMS and GoTo, which are on the mountain, which observe in slightly different wavelengths in different ways. We can work together to hunt these fast transients together. Huntsman is really designed to do this now. Now it has its NVIDIA Jetsons on board. What we can do is take a sort of large picture of the night sky and compare a reference star to a target star and take images on the order of seconds. When you're looking at these really bright objects, you can get enough light to be able to do this and see whether or not you've got any changes in your light curve. And so Huntsman sort of does this in real time using the Jetsons on board, so we can only save the data that we want to keep. Because you can imagine with that many cameras taking images in sub-second exposure times, you've got gigabytes of data coming off this telescope per second. One of the things that, one of the projects we've sort of been working on with Huntsman recently is Deeper, Wider, Faster. This is a group of astronomers working with many different telescopes around the world to try and pinpoint these sort of fast transient objects. And in particular, looking at optical counterparts to fast radio bursts. So one of the things that we do is we shadow the Parkes radio telescope. So Parkes will slew to a place on sky. With a fast radio burst, you've got no idea where it's going to come from. Some of these things repeat, but you have no idea when they're going to repeat. So it's pretty much just point and shoot and see if you can see something. So Parkes will point, they'll tell us where they're looking, and Huntsman will shadow it. And what we're looking for is a flash of light at the same time Parkes sees a radio burst. Now, we haven't seen anything yet, but Huntsman has a bit of a reputation for being the only telescope on sky at the time that the radio bursts do go off. But what we're finding is that we're not seeing them. So this is really interesting. Whether or not it means that Huntsman isn't seeing deep enough, it's not seeing faint enough, or whether or not there isn't an optical counterpart to these bursts, we're not sure. It's still an evolving science question. We really don't know yet. So one of the other things that we're looking at is exoplanets. And we now have a postdoc who is working full-time on this, which is really exciting. In particular, TESS exoplanet follow-up. And there's a bit of a problem that we're seeing with exoplanets, and that's when we're looking at the orbital period of these planets. So planets that are orbiting closer to their host star, that period tends to be faster. And if we look at Jupiter-sized planets versus Saturn-sized planets, so big, what we call big hot Jupiters that are orbiting close to their star, we find that there's actually a missing population of these planets. And so what Jaime is trying to do, which is our postdoc working with us at the moment, is try and see if we can find some of these hot Jupiters, or if we can find these Jupiter-sized planets that are orbiting further out and monitor them and see whether or not their orbit is decaying. And this would give us some evidence of whether or not there are tidal interactions going on between these exoplanets and their stars, which would eventually lead to an evolution of the orbit falling in and essentially being consumed by the host star. There's a bit of a theory that something like that might be going on. We're not sure, and this is hopefully one way that we can find out what's actually going on here. So, of course, our original science case was the low surface brightness universe. And in particular, looking at signatures or these sort of telltale signs of the growth of galaxies over a long period of time. So this is a simulation showing a galaxy sort of similar to the Sombrero galaxy with a little satellite galaxy that's close to it. And what we're going to do is look at this galaxy at different surface brightness limits. So looking fainter and fainter. And what you see is as we get fainter, more structure starts to appear around this galaxy. And what essentially you're seeing is stars and gas that have been stripped away from the galaxy during an interaction with another galaxy. And in this case, it'll be this little dwarf galaxy here on the side. And as you get fainter and fainter, you see more and more. And eventually, all of this information that you would have missed had you just taken one image instead of looking really deep is actually what's telling you, is the trace that's telling you the history of this galaxy and how it was formed and how it's been interacting with the other galaxies and the environment around it. So do we see this in deep fields? Well, we're not seeing it as much as what we would expect. And so what we're trying to understand is, our simulations tell us that we should see this, but we're sort of missing this. And so our simulations aren't matching reality. So are our simulations wrong, or is it that we're just not looking hard enough? Are we missing all of this light because we're not looking deep enough? And some of these shell structures that we see, these sort of stars that are around these galaxies, we are starting to see them in deep images, and you can see there's a bunch of examples here. But trying to see this on a larger scale is something Huntsman will hope to try and understand. Now, seeing the outer edges of these galaxies, for one Canon lens, it takes around 144 hours to see the edges of this image. But with 10 lenses, you get that edge. It only takes about 2 nights to be able to do that when you have 10 times the amount of photons being collected. So this is one of the science cases I'm really interested in, which is pushing the limits. And that's an image of the helix there, and you can see there's a little sneaky satellite going past the frame there. So we can all relate to this now. And I think I remember when I was just starting out as an astronomer, most of the Starlink satellites, the Starlink hadn't been launched yet. So seeing a satellite in the sky or seeing a satellite go through your image was it was an exciting moment because it didn't often happen. But now I think I can't recall a night where I saw no satellites in an image when I wasn't intentionally trying to see them. They always happen now. Thank you, Mr. Musk. And so this isn't a problem for astronomers, but it also presents, I think, an opportunity. What you can see here is an image, sort of a video that we're taking of a star of interest, and we're trying to take lots of short exposures and try and understand what that star is doing. But you also, in the background, you've got these satellites which are streaking through your images. And this, in particular, is a group of Starlink satellites that have just recently been launched. And they're all bunched close together. So you've got one satellite streaking through, another one streaking through, all in the same area. Now, this is annoying for us as astronomers, and what you would usually do is you would throw out these images. But what's interesting is what I found is this is actually really valuable information for a satellite operator. So what those streaks are telling you, if you can measure how long they are, how fast your exposure was, and exactly where they are on the sky by plate solving your image, you can narrow down what the orbit is of that satellite. And when that satellite has just been launched, this is really valuable information for a satellite operator. So there are ways that we can work together. And although they are destroying some of our images as astronomers, hopefully there is a way that we can start to work together. There are things that we can do for them, and hopefully that brings an understanding of what they're doing to our work and how we can work together to find solutions. Now, I guess I got a bit sick of the satellites streaking through my images, and I thought eventually, okay, what if I actually tracked these satellites with Huntsman? What would I see? Would I see anything interesting? And these are 2 satellites that you're probably very familiar with. The one on the right is the International Space Station, and the one on the left is the Chinese Space Station. But what's really incredible about these images is they weren't taken at night. These were taken in broad daylight. So maybe I got a bit sick of observing at night and I just decided to see what I could do during the day. And lo and behold, I found you could observe satellites in broad daylight. And not just Starlink, not just the International Space Station, but you can see Starlink satellites, see things as small as Starlinks that are very bright and visible during the day. It's a pretty shocking thing to think about, because all of a sudden you're like, wow, okay, they're so bright and they're polluting the sky so much that we see them during the day as well. But again, it's another opportunity that we can use to track these objects, work out where they are, and hopefully build that relationship with satellite operators. And that's just an example of an astronomical object observed during the day. That's Venus. And some of us may have already done this. It may not be a surprise to you that you can observe stars in the middle of the day, stars and planets. And indeed, one of the stars I have been observing is Betelgeuse. And this is a light curve of Betelgeuse. I don't know how many variable star observers there are in the audience. But a light curve of Betelgeuse over a couple of years, and you'll notice that there are gaps in that light curve. Now, we had the great dip of 2020 when everyone thought, well, what's happening to Betelgeuse? Is it going to go supernova? And it got really, really faint, but then it jumped up again. If that had occurred when Betelgeuse was only visible in the sky during the day, we would have completely missed this. So what we're doing now is using Huntsman to monitor Betelgeuse all the time. We can take data points even during the day now as well and fill in that light curve. Some more exotic things that we're doing. This is a new type of camera which we're trialing on Huntsman. It's called a neuromorphic camera, or an event-based camera. And what it does is it mimics how the human eye works. And instead of taking an image of a star, say, and sort of collecting the photons and telling you how many photons it's collected, it looks at when the light changes in intensity, and it only reads out a pixel when that light changes above a certain threshold. So what ends up happening is that you end up getting a whole field where there's no data being read out, only where the information is interesting. And this image here is actually of Jupiter and 4 moons here. And you'll notice that the only part of the image where you can see Jupiter is the outer edge, and that's because the seeing is sort of changing the intensity of the object around the outer edges. And this was actually taken during the day as well. So something else I love to do with Huntsman is inspire the next generation of Australian astronomers. Huntsman, for some reason, gets people excited, it gets people interested, and so I like to use that to do outreach. This was on Australia Day Live in 2023, and sort of doing things like making Huntsman pumpkins and things like that. You might have seen some of our media coverage and trying to get people involved in astronomy. And of course, we can observe from live with Huntsman from anywhere in the world. So we do these sort of Huntsman nights, particularly at Macquarie University, where we do astronomy open night and teach people about the sky using Huntsman remotely. So that's it for me today. If you want to learn about any of the other projects or learn more about me, you can scan one of these. If you want to get some software and actually build your own Huntsman, head to the Huntsman telescope. Learn more about Spirit and the work we're doing with that satellite, scan that one, or if you just want to learn a bit more about me. So thank you very much.
Thank you, Sarah. That was a wonderful presentation. I actually, I know Bill, I'm going to bring Bill in, because Bill is on next. I know Bill's a refractor man as well. I am a Newtonian man, so I'm a refractor man. Bill's a reflector man as well. Sorry, no, Bill's a refractor man. I'm a reflector man. That's right.
Other way around. Yeah.
Yes. I noticed in the chat when you said
refractors for the win.
Yeah, refractors for the win, and I'm like reflectors for the win. With your dome, you're saying that it goes out of shape.
Yep.
Does it have bracing internally in it, like ribbing to create bracing?
It does. Yeah, it does.
And it still goes out of shape.
Yeah,
it's an astrodome, isn't it?
Yes.
Yeah.
Yeah, I know a lot of people.
We're actually building one of those at the moment at the ASV's dark sky side.
Okay.
We are, yes.
See how
We've only just got past taking it off the back of the truck. Stage.
No. We've got the ring down. The ring's down. The ring is down. So it's getting there, slowly but surely. Talking about ZWO cameras, I'm a man who has ZWO cameras. I have ASI as well. I love it. I know not everyone does. I love it because of its simplicity. Just plug and play.
Absolutely.
For me, that's great.
Yeah.
And Andy, one of our viewers, Andy, said his ZWO cameras had a very hard life and lives outside all year round. It gets covered for rain, but in summer, when I'm away, I run it remotely and it spends the day in the sun, but with the cooler on. So all up, they are robust cameras. So Andy
Yeah.
lives
I am
out.
impressed.
Andy lives out in near the South Australian border in Victoria, in an area called Langcoop near Edenhope. And so when he goes away for a day or two or three, he literally does. If he knows it's not going to rain, he leaves his telescope out in the sun with the coolers on and the cameras on, so he can remotely log in and image at night. He's a very trusting man, I tell you what.
Yeah, I wouldn't do that.
No, I wouldn't do that either.
Differing opinions as MWO. Yeah, I mean, overall, like using it just as for an astrophotography camera, I do find them to be amazing. They're really simple to use. The software is great. I don't know if we just got unlucky with a bunch of them, but all 10 of ours have had problems eventually. Might be how we're using them, how the power system works. I don't know. But yeah.
Well, there you go. Andy's saying he left it exposed for 5 weeks in one go.
That is brave.
That is very
Andy
brave.
is certifiably insane.
Yeah, he is. He absolutely is, but we love him. Look, Sarah, thank you very much. That was an absolutely wonderful presentation. It really was. I did have another question just about, so when you're talking about the impact of the satellites, I do like the idea of what you're talking about, how you can use it for data. Is that something that can be pushed along into citizen science, for instance?
Look, I'd absolutely love to do something like that. One of the things that we're trying to do is just sort of draw awareness to the fact that it does impact astronomers. I think something that we do is we take these images, we see this impact, and we delete the images, and we don't tell anyone about it. And so the visibility for the problem is not as much as what I would hope it to be. But what satellite operators are doing is they're actually starting to paint their satellites black so that you can't see them at night. Starlink, what they're doing is quite clever. They change the angle of the solar panel when they're going through the terminator so that the light isn't reflected back to the astronomer, and so they're essentially invisible. So there are things that we can do. But unfortunately, that the people who do space domain awareness, we're so scattered and unsure of how to do this. The situation is evolving so quickly. And the need is becoming so huge so quickly that we can't even coordinate ourselves. So there is online databases. There's the Universal Data Library, UDL, which is the American one. And that's sort of where everyone you can get an account there and can put your data online, and satellite operators will see that and use that. So if you want to do it by yourself, absolutely go ahead and have a go. But at the moment, there's no coordinated effort, unfortunately, within sort of the amateur sort of citizen science community to be able to do this. And I think that's a real missed opportunity, particularly when we have situations like last year. At the end of last year in December, we had a breakup of a geostationary satellite. So a large geostationary satellite, it broke up, Intelsat 33E. No one knows why it happened. It was hit by something, if it had a malfunction. And all of a sudden, we had all of this debris in orbit in an area where Australia could see it, and all of a sudden people had to come together to quickly track this stuff to make sure it didn't hit any of these other satellites. So you end up with a cascade effect if that happens. So in those sort of situations, you want as many eyes on the sky as possible. So I absolutely agree. It's a fantastic opportunity for citizen science. It's just we need to get someone together to get it started.
Well, I've just posted the link to the website you spoke about in the comments, so everyone will be able to go there. And because we have a lot of astrophotographers, and we do have a lot of posts in our members only groups for the ASV where people are posting, damn satellites coming through again. And I've seen quite a few videos, time lapses in particular, of night sky where it's just scattered through. In fact, I've taken some myself as well. So yeah.
It's a massive problem, and I'm honestly worried for the future of ground-based astronomy, like things like the Rubin here, right? And it's going to be a real challenge, especially as these satellites get larger and larger. We've got the Bluebird generation of satellites coming out. They're absolutely huge, 200 square meters of surface area, and they're going to be so bright. So we need to really hit this on the head now. Otherwise, we're going to end up with a problem in 10 years' time when there are twice as many satellite constellations.
Probably three times as many in 10 years' time, yeah. It's just going to keep filling up. Sarah, again, thank you very much. It's a wonderful talk. I found it very interesting anyway. I know Bill did. He was, in fact, he was messaging behind the scenes as that, and I've had a few people sending me messages saying how interesting the talk has been. So it's been a wonderful presentation. Thank you very much. We will have to get you back to do some more presentations for us. If you like doing outreach, we're more than happy to have you come back and give another talk.
Yeah,
it'd be lovely to have you. Yeah.
Thank you very much.
Wonderful. Thank you, Sarah. I'm going to, Bill, have you got your screen ready to share? If you'd like to get your presentation up, Bill, I'll pop that on.
Probably.
And then we'll hand it to Bill for this month's What's in the Sky. Here we go.
Can you see that?
Yes, we can. Floor is yours.
Excellent, excellent. All right. Well, okay. Now, first of all, let me say that this is a little bit overdue. It was written to be presented about a week and a bit ago. Some things happened, and so it's not going to be quite as nifty a presentation as it might have been. But anyway, this is for late July or possibly very late July and sort of the first half of August for 2024. I've got the year wrong. Look at that. Isn't that terrible? All right. So tonight, first of all, we are meeting on the lands of the Bunurong and the Wurundjeri Woi-wurrung peoples of the Kulin Nation. Specifically, I am on the lands of the Bunurong. I'm south of the Yarra by about 400 metres. I'm going to speak about the general conditions at this time of the year and the usual format. What's in the sky? Where's the moon? Where are the planets? Some orientations in terms of constellations and bright stars. I'll talk about suggested targets briefly for tonight, and a little bit for the early rises, and then some things to look out for this month. So the general conditions at this time of year: sunset is about 5:15, dark about 6:10. Next month it's going to be about 5:40. So we're going to start getting a little bit lighter next month. Sunrise is about 7:35. It'll be dark until about 6:40 or so. Next month that's 7:12. So again, we're getting a little bit more sunlight. Because we passed the winter solstice, things are going to get a little bit brighter, but they do tend to get colder. And so for the young astronomers, why is this? Oh, no, wrong question. Can you find the equator in the sky? Which hemisphere gets the best view of the Milky Way, north or south? He said, you can figure that one out. It's also Milky Way season. Milky Way is just about directly overhead right now. In fact, if you go outside, in Melbourne, it's cloudy, but the Milky Way is directly above us at the moment. I think it's also moon, but that's okay. Okay, speaking of moon, for the moon people, full moon is on Friday the 11th, which was the other day. Let's not talk about that. I'll go for the last quarter is on Friday the 18th, which is a couple of days away. It's back in the northern hemisphere on the 17th, which means that it'll be closer to the equator. It rises at midnight, sets at noon, and then over the following week it will be a waning crescent. That waning crescent will get thinner and harder to see as it gets closer to the sun, and it's going to be before sunrise and just before the new moon. You view it in the morning, later in this week in the early afternoon, then just before sunrise. New moon is on Friday the 25th, and this is where the astronomers should go out and go to the dark sky site. On DSS in our case, but you can choose your place. You'll see the moon a few days after the new moon as a waxing crescent, and that's when you look west before sunset. First quarter is the Friday, the 1st of August, and it's in the south, which means it will be high in the sky. There is a lunar X coming up. It's 8:47 p.m. It's high in the west. It's a great opportunity this time. I will see if I can get a shot. And also the apogee is on the 2nd, so it's a mini lunar X. I don't know if that has any significance at all. There is another full moon on Saturday, the 9th of August, but we'll probably get to that. Well, I don't like talking about full moons anyway. They're boring. Okay, so the planets. This is from the ASV yearbook. Mercury, it's out of the evening twilight. It's just past its greatest elongation. By the way, about a week ago, I was at Whitefield National Park, and I got a photograph of Mercury a long way from the horizon. It was a fantastic shot. Well, fantastic view. It's Mercury sets about 7:20 in the northwest, so it's a beautiful opportunity for viewing Mercury. Venus is an early morning object. It rises about 20 to 5 in the mornings. It's very, very bright still. It will be a little bit it's starting to move back towards the sun about now. You still can't miss it though. It's the brightest thing around, so you can't miss it. Mars is in the doldrums. It's very slowly moving westwards. It sets about 9:45 p.m. The sun is in the north at the moment, which means Mars is being sort of preserved in the night sky a little bit, but it's spelt wrongly. It should be an apostrophe. It's low. So when we're doing demonstrations from the Melbourne Observatory, Mars is usually gone from our view. It's normally behind either a tree or city buildings. Jupiter is past conjunction, so that means it's a morning object. It's very, very, very hard to see. You have to see it before 7 a.m. It's still in twilight, but it's worth a try. Saturn is an easy post-midnight object now. It rises about 11:15. Best around 5 a.m., which is roughly when it transits. So it's good probably from 3 till breakfast time. Uranus is a morning object. It rises just before 4 a.m. It's not very far from Venus. It's actually quite close to the Pleiades if you can find those. But it's one you do have to wake up in the morning for. Neptune is still very close to Saturn. They will spend the rest of the year very, very close to each other. It's just 1 degree to the north of Saturn. It rises at about the same time, a couple of minutes before. Pluto, which is a planet, it rises after sunset. It's good all night. The opposition is on the 25th of July, so that's coming up. Okay, now this is the sky, 10 p.m, facing south tonight. Actually, the other day, 9th of July. So there's that little clock centered on the south celestial pole. The Southern Cross is at about 2 o'clock on that clock. Obviously, the pointers are about 1. They follow the cross around. There they are. Now, Scorpius is dead overhead, which I normally talk about donut warnings. That's that donut-shaped area, which is good for viewing. The center of the donut is directly overhead, and sometimes you can't hit it, depending on your mount and the size of your telescope and stuff. Orion is our other signpost stars, and that is currently below the horizon. Antares is near the zenith, again, donut warning. Spica is high in the west. Arcturus is north of Spica, high in the northwest. Altair, to find Altair, you start at the cross, hop over the moon in this case, hop over Scorpius, go over twice, and it's off in the northeast. I was about to say the horizon. It's a little bit above the horizon now. It's about sort of 45, maybe 40 degrees. Achernar and Canopus are the stars that I like to follow around that clock. They're both very low on the southern horizon at the moment. They're both hard to see, depending on the time of the night. Later on after midnight, you'll see Achernar coming up, but Canopus is probably behind trees. Fomalhaut, it is rising in east-southeast. So I think that's the first time we've seen Fomalhaut this year. Vega is low in the north-northeast. If you can get a shot of Vega, if you get a look at Vega, it's just a star, but it has a fairly short season around about now. So it's about 2 months. You'll be able to see it in the north, very low. Sagittarius, which is the center of the Milky Way, it's nearing the zenith at now. So that's basically, if you're into getting wide field shots with your camera of Milky Way, now is a great time to get it, because Sagittarius is where the core of the Milky Way is. Okay. So visual targets for tonight. Just a couple of ones chosen largely at random. This is again 10 p.m. facing south. It's the same map. Delta Corvi, which is an optical double, it's getting towards the west. Now, here's a challenge for you. The Blue Planetary Nebula. It's not very far from the Cross. It's a very pretty little thing. It's one of those things that you need a lot of aperture to be able to see, and use averted vision as well. But if you can get a look at it, it's very, very pretty. 5139 Omega Centauri is there. It's probably the best glob that we've got. Possibly, if you're not talking about 47 Tuc. The coal sack is a naked eye object. Please put your telescope away for a little while and get outside and have a look at the coal sack. It's of significance, quite a lot of significance to the First Nation astronomers. Beta Scorpii is a double. It's the left-hand claw, I suppose, of the scorpion. It's worth a look if you've got a telescope with fairly high magnification. It's quite a nice double. 6231. I like to keep on coming back to this. A couple of reasons. First of all, it's very, very easy to find. It's on the back of the Scorpius there. But I love the name, False Comet Nebula. It's an open cluster. It's not a comet and it's not a nebula. So that's, I don't know, that's just me. Easy one to find, M7 Ptolemy cluster. It's on the other side of Scorpius. You can see this with a naked eye if you know where it is. And you don't need very much in the way of instruments. A pair of binoculars is great, particularly from the dark sky side. M6 butterfly cluster not far from M7. It's probably one of the prettiest clusters around, and with just a little bit of imagination, it really does look like a butterfly. It's quite pretty. For the nebula hunters, such as myself, the lagoon is getting very close to transiting at 10 p.m. In fact, tonight would be a really good night. Well, if it weren't for the clouds, to get it, you'll get a lot of hours on that as it goes through, as long as your telescope does a meridian flip correctly. For the more arcane stuff, Barnard Star is available also. It hasn't transited yet. Transits about 11 o'clock or something like that. Barnard Star is one of the closest stars to us, but the great thing about it is it has the highest proper motion, I think, one of the highest proper motions of any star. And you can actually, if you take shots of it year after year, you can actually see it moving quite nicely across the background stars. Brocchi's cluster is this is going to be a binocular thing. It's called the coat hanger because it really does look like a coat hanger. It's very, very large. You probably don't want to use a telescope, certainly not a large telescope. A pair of binoculars is the best thing to find Brocchi's cluster. But yeah, it's a telescope. It's a coat hanger. It's a really freaky thing. Beta Cygni. Alberio, again, like Vega, it's a long way in the north, which means it has a fairly short season. It's a little bit higher at its highest than Vega itself. The great thing about Beta Cygni is it's very, very pretty. It's a double, but it's two very different coloured stars right together. So it makes a beautiful colour. A beautiful color image. If you can get a photograph, you can tell the difference with your naked eye easily, but you will need a telescope with some decent magnification. But I encourage you to have a look at Alberio. Southern Alberio as well, you can't see it at the moment. So photographic targets. Now, sorry, I didn't have time for images for this one, although I possibly could have, because the whole talk got delayed, but yeah, life happened. So time for the Dark Doodad. It's possibly a little bit late for the Dark Doodad, but it's a really, really nice little thing. It's very large. It's larger than my 1.5 puny degrees will handle. You'll need something like 2 or 3 degrees to get the whole thing. It's really, really pretty, dark, and it's that lovely chocolate brown color that you can process out of it. The Dark Wolf Nebula is the Dark Wolf Nebula is, this one's not my favorite. I'll probably get to my favourite one in a second. But the Dark Wolf Nebula is a reflection, and it's quite a complex nebula, but it's in Lupus. I don't know really why they call it Dark Wolf Nebula. This one, which is the Dark Wolf Nebula, this one's Sunquist 17, and this one is super hyper giga exotera cool. It is an amazing piece of nebula. It's really only in hydrogen alpha that you can see much. In a full color camera, it will look okay as long as you're good and sensitive in the infrared. But in hydrogen alpha, it is amazing. So go and find that. From memory, Anne-Marie McComb took the definitive photograph of it a couple of years ago. 4628, the Prawn Nebula is there. That's very, very close to the zenith at the moment. Rho Ophiuchi, if you've got a very wide angle, you'll probably need something like a 15 to 50 millimeter lens. Depends on how much of Barnard 44 and 45, those streamers that go back towards the well, in this case, the moon, back towards the galactic core. But yeah, Rho Ophiuchi is an amazing piece of sky. It's possibly my favorite area in the sky. So many different colors, so many different stuff, different things going on. Beautiful. Pipe Nebula is also there. I'll rattle through these. Dumbbell Nebula is dumbbell season, a little bit like Vega. It's a fairly short season, so have a look at it now. It's a long way to, it's possibly 3 hours before it transits. So tonight you'll probably be able to get 6 hours above, say, 25 degrees altitude on that. It'll be quite a good time to get it. Ring Nebula, like the Dumbbell Nebula, it's short in season, but it's a very pretty little thing. It's a little bit like the Helix Nebula, only sort of, I don't know, ringier. It's a planetary. And also back to Beta Cygni. I haven't seen a decent photograph of this, so I'm sure somebody out there like Jeff Healy, please get a shot of Beta Cygni. It's a beautiful thing. So that's just like putting it out there. Okay. 5 a.m. facing south. This is the sky at 5 a.m. As you notice, the moon and Scorpius is getting towards setting. Let's see. Southern Cross is nearly at 6 o'clock, so it's probably about as low as it gets, depending on where you are. It's probably in the trees. I can't see it from my house at the best of times, but yeah, wouldn't have a hope from here at the moment. Get rid of that. Okay, Scorpius is approaching the horizon, but guess what? We've got Orion back. It's just starting to come up now. There's Rigel and the belt stars, which are right on the equator. They're just rising at 5 o'clock in the morning. So the sun isn't up until sort of 6. So you might be able to get sneaky M42. I don't know. So for planets, we've got some planets in the mornings at the moment. Venus it's starting to go away, but it's good and bright and reasonably high still. Uranus, not very far from Venus. There it is. Saturn is approaching transit at 5 a.m. That's probably its best time. Neptune is very close to Saturn, as you can see. Pluto is just doing its thing. It doesn't move very far because it's a long way away. Okay, so some random observations for this month, the 14th of July, which is gone. Saturn is stationary and it's moving into retrograde. And ask your local astrologer what that means, and then you can ignore what he says, or she. 25th of July, Pluto's opposition. So if you want that photograph, it's a good time for it. Pluto will be probably not an awful lot brighter than it is normally, but opposition is technically the brightest time. So what you do, you take a photograph, then come back a week later, take a second photograph, and compare them. And the one that moves, that's Pluto. Remember the 1st of August, Lunar X 2047. It's high in the west. Beautiful opportunity. I'll have to remember. 9th of August is Vactrock. And now Vactrock, I think I'm going to be there. Dylan O'Donnell will be there, and a whole pile of other people will be there. So basically, what you should do is be there. 11th of August, Mercury is stationary. It moves out of retrograde, which for the inferior planets, it doesn't actually mean an awful lot because they just go left and right and left and right and left and right all the time. So anyway, it's stationary. 12th of August, Venus and Jupiter, they are going to be having a bit of a powwow. Look northeast at 6 a.m. Both of them are bright planets, so you should have no trouble finding them at all. Venus is going one way, Jupiter is going the other. They're actually going to pass each other in the sky. And there we go. Sources and big logo. Thank you very much.
Sources and big logo. I like it.
That's what it is.
Now, Bill, I think the only time the astrologers get concerned is when Uranus goes into retrograde. Sorry, I had to put it in there. I couldn't help myself.
I do have a lot of respect for astrology because that's where we got astronomy. Don't forget that.
Yeah. Sometimes some good things do come from bad things. Hey,
something like that. Yeah.
Something like that. Yeah. So yes, you're right, Vastrock. We have. Hang on. Do you want me to?
Yeah, I'm just going to stop that.
Yeah. Stop that. Otherwise, we're going into. I've forgotten what that movie was. Inception. We're going into Inception. That's it. Yeah.
By the way, that last photograph was my late friend Dean Hewish, Dr. Hewish. He passed away a couple of weeks ago, and so I just thought I'd just remember that. So
no,
that was him
fine,
taken at Lake
fine.
Acroman.
And as you know, my condolences. We do have Bill Stent, the telescope gent, giving his What's in the Sky live at Vastrock, which is down in Geelong. And Dylan O'Donnell is going to be there, and so is Eileen O'Healy, and so will Dwayne Hamaker and Alex Cherney and Chris Morley and Trevor Hand and Bruno Zelke and Kelly Clitheroe as well. We've got a heap of speakers coming down for Vastrock. And Sarah, if you're available, if you want to put your hand up, I'll send you an email separately about it. We'd love to have you down there too. Actually,
you can do the What's in the Sky talk.
I'm just dobbing you in right now, isn't it? You know, live on stream, so you can't say no. No, well, I'll shoot you some details. I think would be great if we could have you down there as well. It'd be wonderful. We do have a little bit of room left, which is great. If you're interested.
Yeah, it sounds awesome. I miss getting out there in the field. I honestly do.
Oh, this one will be a good one. It's down in Geelong. So,
it is the night of the full moon, though.
It is the night of the full moon, but that's exactly why we're doing it on that weekend, because nobody's going to be doing any astronomy anyway.
That's true.
Yeah. It's a perfect weekend for Vastrock. Tickets are on the website, on the ASV website, asv.org.au. If you go to the events page, you will see Vastrock there. You'll also notice that Sea Lake is now live and up and running, and the Q&A dinner and the quiz will be up and running soon, and so will the links for the speakers as well. But all of the other events are all live, and you can book them now as well for Sea Lake on the grand final long weekend. For those of us who are not concerned about football, I mean, I am, but I'm willing to forgo the fact that Collingwood's probably going to win the flag this year, and I won't get to watch it, but that's okay. Anyway. Great talk, Sarah. Great presentation again, Bill, even though it was a condensed version. As usual, I will chop down Bill's What's in the Sky and upload that separately as a video onto our YouTube page for everyone to see. And so you can go back and listen to Bill again talk about retrograde and astrology. And no T Corona Borealis this month, Bill. What's going on? Are you feeling okay?
Well, it's been cloudy.
It has been a horrid month for astrophotography and for astronomy in general, hasn't it?
It has been. Remember that there is another recurrent nova which has gone off. I've forgotten its name. He says, but I got the shot of it being there. The thing that I have to do now is take the reference shot, which is I'm going to cheat and have it like about now. Hopefully, it won't be there, but we'll see.
We'll see. Anyway, wonderful. Thank you, everybody, for joining us tonight. We'll be back in about 3 weeks' time. I'm very confident we have Duncan Wright from the University of Southern Queensland giving us a talk about Mount Kent Observatory and all of the wonderful things that they do up there. So we'll see you back here in about 3 weeks' time. Live stream only again because Lightscape is still on at the Royal Botanic Gardens Modern Museum, so we can't use the venue there. So it'll be live online, YouTube, Twitch, and Facebook again. So we'll see you guys then.